Hello, and I welcome you all to the revision of the Electrotechnics N6 paper that was written August 2024. Right, so without wasting much of the time, let me quickly go straight into the revision. So I will skip the instructions for the sake of time and progress, but I do advise when you're in the exam to go through them. It's very, very important. Right, so the first question there was saying a DC series motor is a variable speed motor. Explain using suitable formulae why the current drawn by this motor increases when it's mechanically loaded. Right. There is something that I needed to point out quickly in this question, that it's one of the recurring questions that we have that finds itself in many papers. For example, if you go to the November 2023 paper, you will find the same question again. So such questions, I advise not to ignore them. It's very, very important that we understand them. So let's just quickly answer the question there. So they said with the aid of suitable formulae. So let us indicate. Right. So number one, using the formula IA is equals to V minus E over RA. Knowing again that E is equal to K times N multiplied by phi, where K is the motor constant, and of course N is the speed, and phi is the flux. So we say when motor is loaded, the speed N decreases, resulting in the EMF also decreasing, and therefore IA increasing. That's the explanation that we need with the aid of these two formulae that we have, right? So that's basically 1.1 that I've just answered there. Let's quickly go to 1.2. So I'm advising that questions of this nature that tends to find themselves in appearing in quite a number of papers. There are a lot of such questions that do come. Kindly understand them. It's very, very important that we do so. Right. So 1.1.2, the next question is saying a 200 volts DC shunt motor operating at full load speed of 1,000 revolves per minute and an efficiency of 82% delivers 10 kilowatts to a certain load. The resistances of the shunt field and the armature circuits are 100 ohms and 0.2 ohms respectively. Assuming a straight line magnetization curve and neglecting the effects of armature reaction, calculate number 1.2.1 the speed at which the motor will run at no load if the electrical power input during the condition is 1 kilowatt. So this is the information we've been given. Right, so let's quickly answer this question. First things first, I advise, right, of course, for the sake of illustration here, I will try to indicate the diagram that we have. Okay, so there we are. That's our shunt field winding, and that's our armature. Okay, then we indicate this as our first conditions. So we have a terminal voltage there of 200 volts we have been given, and of course PI at no load 1 kilowatt, and of course IF. So we are saying we have IF1 there, and we have IA1, right? Mind you, this is a motor, so we have, of course, IL1 there, right? And then we have P out, and of course, that's our diagram there, right? Okay, let me just quickly highlight. Okay, so there is our diagram, right? Secondly, we have the new conditions now that arises at full load. Right, there is our field winding. There is our field winding again. There is our armature. There is our armature there. Right, let me try to invite this a little bit. Okay. All right. Right. So there is our diagram. Okay. Then, of course, this is our P out. This is our P out. Right, that's P out there of 10 kilowatts we've been given apparently. That's our P out. That's 10 kilowatts. By the way, the P out here, it becomes 0. Remember, I said no load, 0. right? So this is 10 kilowatts as a P out. And then N2, here we have been given at full load, we were told is 1000 revs per watt per minute. That's the information we have. Then here, N1, apparently we do not know. That's practically what the question is asking, the speed at which the motor will run at no load if the electrical power input during the condition is 1 kilowatt, right? So we do not have the N1, that's the one we're looking for, right? So this is the information that we have. We want now to use this particular information to answer our question, right? So let's start with the no load, P in there. Let's retrace. How do we find P in the first place? P is equal to V multiplied by IL1, right? So making IL1 the subject, what is our intention? We want to find IA1 from there. So IL1 is going to be equal to P in over V. So apparently that's 1 kilo, that's 1,000 divided by our voltage, 200 volts. It's going to give us 5 amperes, right? So we have IL1, which is this particular value here, this one. We now have it, it's in 5 amperes, right? And then the next thing that we want is the E1, right? E1 is equal to, okay, we need IA1 first. Let's first calculate IA1 because for us to find, remember, it's a shunt machine, it's V minus IA. So since it's E1, it means we are saying V minus IA1 times RA, the armature resistance. So we still need IA1. How do we find IA1? Right, we go back here. According to Kirchhoff's first law, IL1 is equal to IA1 plus IF1. So basically that's kind of straightforward then. So it means IA1 is going to be equal to IL1 minus IF1, right? But do we have IF1, which is our shunt field current? Apparently, as it stands, we do not have it, but can we find it? Okay, we know that shunt, which is IF1, is equal to V over R shunt, of course, the shunt field winding, shunt field resistance. So that's 200 divided by 100, we have been given as 100 ohms. So that's 1 ampere. So we can therefore safely come and substitute to say 5 minus, so that's in 200 divided by 100, that's 2 amperes. Sorry about that. So that's 2 there, right? So 5 minus 2, that will give us now 3 amperes, right? So we have our IA1, which means now we can go straight into the formula and then substitute to find E1. So what is going to be our E1? That's 200, our terminal voltage V, minus IA1, which is 3 times RA. Remember, the armature resistance we have been given, that's 0.2. So practically here, nothing much is happening except the already known information from the previous levels. But of course, we need now to apply it in the speed control of the DC motors. Okay, so that's E1 there. We have determined E1 as, let's punch, if we punch this on the calculator, that will give us 199.4 volts. Okay, so that marks our E1, right? Let's go to for full load conditions, right? For full load, we have been given apparently the output power. We don't have the input power. We have been given the output power, but in the same sense, we have also been given the efficiency. They say that the efficiency is 82% at that full load condition. So for that reason, we can therefore determine the P in from that formula. So efficiency is equal to, it should be known, efficiency is the ratio between the output and the input. So making P in the subject, it means, so we are saying therefore, P in is equal to P out over efficiency. So this is efficiency times 100, right? So we can just divide that by 100, the efficiency, and it then gives us 0.82, right? So let's substitute, that's P out 10,000, okay, divided by 0.82, and that will give us 12,195.122 to 3 decimal places watts. That marks our P in. Why do we need our P in? Because we can still repeat ourselves to find the P out, to find IL2, which is the full load current. So IL2 is therefore equal to P in over V, like what we did there, right? So 12,195.122 divided by 200, and that will give us 60.976 amperes. Okay, that's our IL2, right? With that, now we can therefore find IA2, right? IA2 is going to be equal to, right? Has the field winding been added to something or anything? Nothing. It's still the same field winding that we had, which we had the current of 2 amperes. So it means the current has not changed. So we can safely say now 60.976 minus 2. And punching that on the calculator to give us 58.97 what? 0.976. That marks our IA2. So with these new conditions, it means we can now calculate E2. So E2 is equal to V minus IA2 times RA. Right, the armature resistance has also not been affected in any way. So we can therefore substitute our formula, our information, 200 minus 58.976. Multiply that by 0.2, and it will definitely give us 188.205 volts. So we have E1, the no load EMF, the back EMF. We have E2, the full load back EMF. It means from there now we can go into the formula E1 over E2 is equal to N1 IF1 over N2 IF2, right? As a matter of fact, I would advise, if you are wondering why are we saying IF, often do we have to say phi? Why would we say that? It's because IF, the field winding, the field current actually is equal to the flux, the magnetic flux in the circuit. So it's good if you find this a little bit of a challenge. I have also prepared a certain tutorial on the speed control for DC motors. You can as well check on it. It's explaining all this. Right, so having indicated that, it means, remember, of course, we are saying IF is equal to phi, right? So making N1 the subject in this scenario, it means we are just cross multiplying there. We get E1 multiplied by N2 times IF2, right, is equal to N1 IF1 multiplied by what? By E2. So we can now divide by IF1 times E2 divided by IF1 times E2, right? So that will now give us N1. N1 therefore is equal to, right, N1 specifically is equal to E1 N2 IF2 divided by IF1 times E2, right? But of course, we know that IF1 and IF2 are actually equal in this regard. So if you notice that soon, it also saves you time to just discard or leave it. You know that they will cancel each other. So I'm now substituting, right? E1, we have calculated 199.4 times N2 we had been given. That's our float speed multiplied by 2 divided by IF1 again. That's 2 multiplied by E2. We just calculate 188.205, right? Punching that on the calculator, it will then give us a speed of that marks our no load speed of 1,000. So we are saying N1 therefore is equals to 1,059.483 to 3 decimal places revs per minute. That marks our N1, the no load speed. All right, so with that, it means we have answered question 1.2.1, the speed at which the motor will run no load. And the next question is saying, determine the resistance, calculate the resistance of the resistor to be added in series with the armature circuit in order to reduce the speed of the motor to 800 revs per minute. Assume that the torque now is 80% of the full load torque. So it means that now there's a deviation or there's a change in values from the full load speed to a new speed of 850 revs per minute. So we are going to call the full load speed our E1, our N1, and the EMF at full load, we'll call it again the E1, and the armature current at full load, we'll call it also A1. So it's a choice that we are making. And then we make these new changes that have occurred. Our new speed that we now have at 80% of the full load torque, we now call them our second scenarios or second situations that we have. So we will call this 850, our N2, similar with its back EMF, also call it E2. So let's try to perform calculation on that. Right. So I'll just clear off the screen. Right. Number one, having or remembering that E1 over E2, right, is equal to N1 IF1 over N2 IF2, right? So it means making E2 the subject, E2 is going to be equal to E1 times N2 IF2 divided by N1 times IF1, right? This is what we have. We have made E2 the subject, right? So substituting what we have, because right now we have E1, remember that's the full load back EMF, and N2, that's the full load speed as well. So substituting that, I said N2 is actually the new speed that we have after the resistor has been inserted or a new resistor has been added. So 188.205 multiplying N2, remember, right, it's 805. So I'm saying, just for interest sake, so that we can follow closely, I said E1 is the full load back EMF, which is 188.205, right? And the N1, that becomes 1,000, the full load speed. And then our N2 is the speed we have been given, which is 805 revs per minute. And of course, we now are looking for E2, the back EMF, the EMF at the new speed that we have, right? So we have just substituted the values there. So we are saying 805, right? Multiply that by 2, of course, that's our IF2. The shunt field current is not changed, right? Divided by 1,000, right? Multiply by what? Multiply by 2. And that will give us 159.97974 volts, right? And then it means we can now go into the formula to substitute, but we also need the current. So from the information we've been given, that the torque is now 80% of the full load torque. It means T2 is now equal to 0.8 of T1. What is our T1? The torque at full load, remember, right? So using again the ratio T1 over T2, T1 over T2 is equal to IA1 IF1 over IA2 IF2, right? It means since T2 is equal to 0.8 of T1, it means we can just substitute that again to say T1 over 0.8 of T1 is equal to IA1, we have it, that's 58.976 times 2 over IA2, apparently we do not have it, multiplied by IF2. What is our IA2? The armature current at the new speed that has arisen after the insertion of the additional the sub IA2. It means cross multiplication and making it a subject. It means we end up having 47.181 amperes, right? That marks our IA2 there, right? Having calculated IA2, let us then calculate the size of the resistor that has to be inserted now. Where are we taking this from? E2 is equal to V minus IA2 multiplying RA plus RX, the resistor that must be inserted in series with the armature. Remember, it has to be inserted in series with the armature. So it means this is where our E2 was actually determined from and our IA2 as well. So we can now substitute what we have. 159, remember, that's our new back EMF there. 159. Okay, let me just indicate it correctly. All right, so that's 159 there, 0.974 is equal to 200 minus, right, 47.181 that we've just calculated, multiplied by RA, we have it at 0.2 plus RX, the unknown resistor that must be inserted in series. So we have substituted everything. We can then simplify now. Right. If we can, of course, just transpose 47.181, it becomes positive bracket 0.2 plus Rx is equal to 200 minus 159.974, right? Then we divide by 47.181. We divide by 47.181, right? It means we end up having 0.2 plus Rx is equal to the value that we get here. If we punch this on the calculator, we get 0.848, right? And then we make Rx the subject. Then, of course, by subtracting 0.848 minus 0.2, right? And that will give us 0.648 ohms. That becomes the size of the resistor that must be inserted in series. So it's very important. If it was, we were told that it will be inserted in parallel, it means we were going to make, of course, a product of what? Over some calculation here. But because it's in series, so that's why we added them, right? So it's important to also take note of that. Let's quickly go to question number 2, right? Question number 2 is saying, a 250 ohm resistor is connected in parallel with the 15 microfarad capacitor. This parallel combination is then connected in series with an inductor having a resistance of 8 ohms and an inductance of 40 millihenries. An EMF of E is equal to 120 sine 314 t minus 60 degrees plus 10 sine 942 t plus 30 degrees is connected across the circuit. Determine the following, of course, the first, an expression for the instantaneous value of the current. Right. First things first, from the information that we are given, of course, the first one becomes our fundamental in this, right? Identifying which harmonic is this one. We can identify it using the frequency here. If we take 942, divide by the frequency for the fundamental, 314, and that will give us 3, which means this one is the third harmonic. We can do the same if they were all even there, if there were 3 of them, or maybe if there were 4. We were simply going to, if we're having another one maybe ahead, we're simply going to do that again to identify which harmonic is it. So we have the fundamental and then the third harmonic, right? To make it clearer for us, it's good that we demonstrate or we represent this information here on a diagram. The information we've been given right here, we can indicate it on the diagram, right? How is it gonna be, right? This is the diagram we have. We are told that the resistor 250 ohm is in parallel with a capacitor. So indicate that the 15 microfarad capacitor, right? So we will call this our ZA. We will call this our ZB for clarity and trying to make our calculations a little bit easier in performing them. Then we are told that they are both in series with a resistor and an inductor, we can as well indicate them. Right, we have 8 ohm resistor and we have a 40 millihenry inductor. Remember, our capacitor here is 15 microfarad and our 250 ohm resistor is here. Right, so we have labeled this one ZA, we have labeled this one ZB. We shall label also this one our ZC. The inductor is having a resistance, a resistor, and what an inductance. Right. So first things first, we can first calculate ZA. ZA is going to be equal to 250 plus, we don't see inductance or capacitance there on the ZA, so it means it's going to be 250 plus J0, which apparently in polar is going to be 250 angle of 0 degrees. Let's go again to ZB, but in order to find ZB, we need XC1, right? So we will first have to calculate XC1, right? Our XC1 shall be given by 1 over omega C, right? Remember, it's 1 over 2 pi FC, right? 2 pi F multiplied by T. 2 pi Ft is our angular velocity, and apparently it is the one given in our waveform, in our sinusoidal waveform, even on the fundamental there. So we use the fundamental 1 over WC omega C, which is going to be 1 over, therefore in that regard, it's going to be 1 over 314. Where are we getting it from? From our expression for the voltage. So it's 314 multiplied by right, the frequent the capacitance, that's 15 times 10 to the power of negative 6 micro, right? So if we punch that on the calculator, it's going to give us 212.314 ohms. That marks the capacitance, and apparently it marks our XC1. What are we now doing? What we are doing now is we have the fundamental on our expression there, and we also have the third harmonic. How did we identify that it is the third harmonic? Remember what I have done there. 940 that's in 942 divided by 314, and that gave us that value, right? So it means I will indicate this as my fundamental, right? And I will indicate the third harmonic there, right? So I'll just try to make a boundary. I would normally advise also to do that just to present your work a little bit clearer, right? That's our third harmonic there. Okay, right. So we are saying for the first harmonic, XC1 is this value, right? It means, therefore, ZB can be found. ZB is going to be equal to 0 minus J 212.314. And in polar, that's 212.314 angle of what? Of negative 90. You just say shift pole on the calculator and you can punch that. You obviously get that, but I advise, especially when the real component is 0 here, you can just do that directly by inspection. It saves you also time. Right, let's go to the third harmonic in that regards. We just do them. Okay, let's first finish off the fundamental first. Okay, so where are we heading now? We would want the equivalent resistance of the ZA and ZB. Apparently they are parallel, so it means it's product over sum. So we need the sum ZA plus ZB, so that we divide into ZA times ZB. So ZA plus ZB, of course, is 250 plus J, 250 plus J0 plus what? Plus in 0 minus J 212.314. There we go. So we are adding this, and it's going to give us 250 minus J 212.314. Converting that to polar, that will give us 327.99 angle of negative 40.34. So we have ZA plus ZB. Then it means we can now calculate ZA times ZB over ZA plus ZB, right? So it means 250 angle of 0 times 212.314 angle of 90, angle of negative 90, that's negative 90 there, right? Divided by 327.99 angle of negative 40.34 that we just calculated. That's our ZA plus ZB apparently. So simplifying that, the top part first, it gives us 53,078.5 angle of negative 90 divided by 327.99 angle of negative 40.34. I hope we are understanding there that, of course, in multiplication, we multiply 250 times 212.314. Of course, we now add 0 plus minus 90. That's where we got that minus 90. And of course, that's where we got that 53,078.5. Now we divide again. We divide in the same sense, right? We divide this, and that is going to give us, of course, 53,078 divided by 327.99, and that's 161.829629, which is 161.83 to 3 decimal places, right? Angle of minus 90 minus 40.34, so that gives us minus 49 minus 49.66, right? So that marks our ZA plus ZB. So we are going to call it ZP1, therefore. Right, let's go to the third harmonic. Let's start with the third harmonic, right? First things first, we start with the ZA on the third harmonic. Apparently, ZA, it is the resistance. Resistance doesn't change. So it is still 250 plus J0, which is 250 angle of what? Of 0 degrees. It hasn't changed. Ohms, it hasn't changed. Right, then we go to XC3. Right, XC3 is going to be given by XC1 divided by 3. That's how it works for capacitance. For capacitive reactance, actually, we divide it by 3, right? So XC1 divided by 3, right? And of course, we already have XC1 there. So since we already have XC1, we are simply going to divide it 212.314, divide that by 3, and that will give us 70.771 ohms. That marks our XC3, right? And then we, of course, it can lead us now to ZB. ZB, therefore, is 0 minus J 70.771, right? And converting that to polar, it means it's 70.771 angle of what? Of negative 19, right? So it means also we need ZA plus ZB for the third harmonic. So ZA plus ZB for the third harmonic is going to be equal to, right, 250 plus J 0, right? I advise whenever you are dealing with the complex numbers, convert both polar and rectangular. It saves you a lot of time. You'll be just using the relevant form. Is it rectangular that you want, or is it polar that you want? You are just taking it and you are using it now. Plus, So we also take 0 minus J70.771, right? And that will give us 250 minus J70.771. And simply changing that to polar, that will give us 259.824, angle of negative 15.806, right? That's our ZA plus ZB, which means, therefore, we are now going to calculate ZA ZB over ZA plus ZB, the product over sum, to calculate what? ZP3. That's what we want to calculate now. Right, so from there, in calculating ZP3, that's ZA ZB, which means we are just ZA ZB over ZA plus ZB, right? So that's in 250 multiplied by 250 angle of 0 multiplying 70.71 angle of negative 90. That will give us 17,692.752, right? So we just substitute that 17,692.752 angle of what? Of negative 90, right? Divided by 259, we've just determined it there, 0.824, angle of negative 15.806, right? And that was giving us, simplifying, 68.045, angle of negative 74.194. Right, so we have ZP1, we have ZP3. Let's go back to the fundamental. ZP1 is now in series with ZC, considering our circuit. This is how our circuit is. It means the ZP1 that we have calculated is in series with ZC. So in order to find Z total for the fundamental, ZT, therefore, is going to be equal to ZP1 plus ZC, right? So we are just taking them directly. ZP1, we need it in rectangular, which means we are just taking, if we add 104.756 minus J 123.35 plus ZC, we have it as well. It's in 8 plus, what's happening now? We have to take XL1 and convert it, right? So that we just move along together, let me just quickly erase this first part so that I start with XL1, right? So we say XL1, right, is equal to, of course, omega L, right? Remember 2 pi F, that's our omega, right? So it's in 314, 2 pi F, that's our angular frequency, right? 314 multiplied by 40 times 10 to the power of negative 3, and that's giving us 12.56. So it means ZC is therefore equal to 8 plus J what? J 12.56. So we already have ZC. And having converted this one to write our ZP1 that we got initially, if we convert it, 161.83 angle of negative 49.66. If we convert it to rectangular, that's 104.756 minus J 123.35. So as I was encouraging to say, always first do that, right? And it saves you a lot of time in the exam, right? So it means, therefore, we are just going straight into calculating ZT with the new values that we have. So we are saying 104.756 minus J 123.35 0.35, right? Plus what? ZC that we have, because they are in series, remember? 8 plus J 12.5 what? 56, right? If we add this, it's going to give us 112.756, right? Minus J 110.79, right? Converting that to polar, that will be 158.077, angle of 44.496 degrees, right? So we have our ZT for the fundamental. Let's do the same for the third harmonic. Right, so number one, we need XL. Okay, let's first just quickly convert this to rectangular. That's it's going to be 18.548 minus J65.52, right? So let's now calculate XL3. Right, XL3 is going to be multiplied by 3. Why? Because we are in the third harmonic. So it's 3 times XL1. So mark that XC, it's XC over the harmonic. Is it the third or the fourth? The third divided by 3, the fifth divided by 5, etc. So for inductive reactance, we now multiply. So 3 times the reactance that we got for the fundamental is 12.53, and that gives us 37.68 ohms, right? So it means our new ZC is going to be equal to 8 plus, so that's 8 there, plus J 37.68, right? So Z3 therefore is equal to ZP3 plus ZC, right? Which means we can therefore say 18.548 minus J 65.52, right, plus our ZC 8 plus J 37.68. There we are. So we are adding this, and it's going to give us 26.548 minus J 27.84, right? Converting that to polar, it means we now have 38.469 angle of negative 46.361, which means that's our ZP, that's our ZT3, right? Right, having done that, it means we have Z3, we now have Z1. Right, with that, it means we can now create the expression for current. It's going to be equal to 120, our E, divided by Z1. E1 divided by Z1, which we got as 158.077. Sine, right, sine omega T, 314T, minus, what was the phase angle, minus 60, right, minus the phase angle that we got for our impedance there. That's negative 44.96. So it is the one we now 44.96. This is the procedure that we follow, right? So apparently this is what we now have. Plus we go to the third harmonic. Just my space, I'm going to write here down. Okay, 10 divided by 38.49, that's our Z3 apparently. Sine what? 942T, right? Plus 30, that was our phase angle, right? Minus, what is the angle of the impedance? Minus 46.361. That's what we got there. Right, so we can now divide that. So it means I is equal to 0.759 sine 314T, right? We now simplify this. It will give us minus 15.504, right? Plus 0.26 sine 942 t plus 17, right? I'll just try to write on the same, right? So that's t plus 76.361, simplification of 30 minus that, right? 7361 amperes. That now marks our expression for the current. We have answered that first question, 2.1, the expression for the current. Right. Let's quickly go to the next. The next question is saying, calculate the power factor of the circuit if the true power is 33.381. That's our next question there. That's 2.2. Right. So in calculating it, we would want the ERMS and the IRMS. So let's start from there. So I'll just erase my screen here. Right. So 2.2 ERMS is equal to the square root of 120 squared plus 10 squared divided by 2. What are we doing? We are taking the Emax 1 squared plus Emax 2 squared divided by what? Emax 3 divided by 2, right? And that gives us 18.147 volts. Let's go to IRMS. IRMS, it also follows. It is the square root of, I hope we are following this from the expression. That's where we took that 120 and this 10, right? And then we go to the expression for current again, 0.759 squared plus 0.26 squared divided by what? By 2. And that will give us 0.567 amperes, right? So it means cos phi, the phase angle, is equal to P, the true power, over ERMS times ERMS multiplied by IRMS. What are we doing? Cos phi, the power factor, is equal to true power over apparent power. So to calculate apparent power S, it's equal to ERMS times IRMS, right? That's what we have done then. So true power is 33.381 divided by the apparent power, 85.147 times 0.567. That's what we are having there, right? So we can therefore use that. Remember, the true power has been given, 33.381, so nothing much is happening. So we can now simplify this, and that gives us 0.691 leading. That's our phase angle there. All right. That marks our phase angle. Now, just out of interest, how did we come up with the leading? How did we know that? So to check the nature of the power factor, always you are using Imax. You check what Imax is doing with respect. Imax 1 is doing with respect to Imax to Emax 1. Right, I'm talking of the two expressions that we have, the expression for current and the expression for voltage. So you are simply checking Emax 1 and Imax 1 and demonstrate, explain there. You are having the reference there. Right, so here is what is happening. We have been told from the first, right, that Imax 1, we did calculate Imax 1, we got the phase angle as 15. Right, we got our phase angle as negative 15.50. So we can indicate it here, right? Somewhere here. That's our minus 15, there it is. So we can indicate it as 15.504 in this quadrant here, right? That's our Imax 1. We'll label it Imax 1, right? And then we have Emax 1. Emax 1 we have actually been given. We were told it's it's having a phase angle of minus 60. So we can also indicate it here. There it is. That's Mx1 there, somewhere here, with its phase angle of 60, because it's negative 60. So they are both in this quadrant, so I'll indicate it here as 60 degrees, right? And in Mx1. So just the whole vector diagram, I'll just indicate all of it. Now, Mx3, we are told it's in 30 degrees. So I can indicate it here. That's my Mx3, right? There is the 30, it's positive, so it's in this in anti-clockwise. Remember, when we are going in the anti-clockwise, that's positive. Clockwise, that's negative on the velocity vector on the vector diagram. Right. So this is our 30, right, degrees. That's our Mx3. That marks Mx3. Right. Let's go to Imx3. Right. Imx3, from the expression for the instantaneous current, we got it as 76.361. So we can indicate it also. It's now here. That's our Imx3. So it's going for 76.361. Right. So what do you focus on? You focus on these two only, Imx1, and you check what is it doing with Imx1. So going in the anti-clockwise direction, you can see that Imx1 is ahead of Imx1. Therefore, for that reason, it's a leading phase angle. When current is leading the voltage, we say it's a leading. You see this, it's showing us that voltage Mx1 is lagging, while current Imx1 is actually leading. So that's where we came up with the leading phase angle, this one. That's how we knew it, right? So basically, this is what is happening. Let's go to 2.3, right? 2.3, it's saying determine the energy dissipated in the circuit in 20 milliseconds. That's our information, right? Energy E is equal to P times T. So the power we have been given, 33.381, multiplied by 20 millis times 10 to the power of negative 3. So that is 0.66762, which is 0.668 joules, right? That's basically our energy there. Let's assume, just out of interest, I think I've answered question number 2. I just want to digress a little to say, if the power was not given, to calculate the power if the power was not given. You see, our power here was given, this one, we're given 33.38. So my question is, what if it had not been given? We were going to calculate from the formula, power is equal to Mx1 times Imx1. From the two expressions, the one for voltage and the one for current, we did calculate at 2.1. So you say Mx1 times Imx1 multiplied by cos phi 1 plus Mx, in our case, is Mx3 times Imx time multiplied by Imx3 divided by 2 times cos phi 3. That's how we calculate that power, right? That was going to be our formula to calculate that this power had the power not been given, right? Where phi 1 and phi 2, this phi 3, so this 2, this one and this one, right? They are the angles between the respective voltage and current vectors found using the vector diagram. This particular vector diagram here, the angles that lie between them are the phi 1 and the phi 3. That's how we do it, right? So basically, this is what is happening. Let's quickly go to question number 3, right? Question number 3 is saying, explain why a transformer is rated kVA. Question number 3.1. Explain why a transformer is rated in kVA and not in kilowatts. Right. It is all because constant losses, which are the iron losses, occurring in the transformer are voltage dependent. And all variable losses, which are often copper losses, are current dependent. Therefore, the total losses depend on the voltage, on the volt ampere, which is VA, and not on the phase angle between the voltage and current. That's why we rate transformers in kVA. It's very important to note that. Right, now here comes the question. Is saying state two constant losses occurring in a transformer. That's our, right. So basically in a transformer, our losses are of course classified as constant and some as variable losses, of course, right? So the losses that we have in the transformer, we have the eddy current losses, we have the hysteresis losses, we have the dielectric losses. These are the losses that we have that are constant, the constant losses that we have. Right, just out of interest, I might want also to indicate where do they occur. Right, the eddy current losses, they occur in the iron core, as well as the two windings, the primary and the secondary, right, due to the circulating currents. That's the eddy current losses. Then the hysteresis losses, they occur in the iron core of the transformer, and the dielectric losses, they occur in the insulating materials of the transformer, right? The insulating materials of the transformer, right? So just out of interest, no one is asking that. I'm just digressing a little to explain that part. 3.2 has been answered. Let's go to 3.3, right? 3.3 is saying a 250 kVA single phase 50 Hz transformer working at unity power factor has an efficiency of 95% at both half load and full load. Calculate the iron losses and the full load copper losses. Right. It might interest us to know that at any load, efficiency can be calculated by, we can calculate efficiency at any load using this formula here. Efficiency for a transformer is equal to K multiplied by S cos phi or cos theta divided by K times S cos theta plus the constant losses. The constant losses, so we are saying this, the constant losses plus the variable losses. These are the two losses that we have. As a matter of fact, it might interest us to know that we do not have frictional force. We do not have the frictional forces on the frictional force on the frictional losses. We do not have them, the frictional losses on the transformer, because it doesn't have any rotating parts, right? So there we are. We are saying constant losses plus the variable losses. And the constant losses are the open circuit power, P out, and also that's variable losses are given by K squared multiplied by the short circuit power PSC, right? So the variable losses are actually also equal to PSC, and the constant losses are also equal to P out. It's also important to know the P open, the open circuit power, where this K is a factor of full load, and at no load is equal to 0. It's good to know that K at no load is equal to 0, and at full load it's equal to 1. When we are at full load, K is equal to 1, right? And at half load, K is equal to 0.5. At say 80%, K is going to be equal to 0.8, or at 70%, K is going to be equal to 0.7. However, at maximum efficiency, K is given by the square root of the open circuit power divided by the short circuit power P out, P O over PSC. Remember, open circuit power is the constant losses, and the short circuit power is the variable losses, right? So this is now straightforward. Let's now go to answer our question. So with this in mind, let's now answer our given question, right? First things first, let's consider the circumstances at half load. Let's start with at half load, right? At half load, now that we know this formula, let's now directly say at half load efficiency, from the formula efficiency is cos ks cos phi. Let's now substitute efficiency. We have it. We have been given. They said at half load the efficiency is 95%. So 0.95 per unit is equal to, right, K, since it's half load is 0.5 multiplied by S, we have it is 250, right, multiplied by 1 kVA. We are just leaving it as 250 kVA. We are not saying times 10 to the power of 3, so because we it's still, even in the denominator, we still have it as well, right? So we are just taking that advantage. We can just use it as it is in kVA, like that, right? Divided by 0.5 multiplying by 250 times cos, remember, cos theta at unit power factor, cos theta is 1. So basically, there is nothing much that is happening. The plus, right? We don't have the constant losses, neither do we have the variable losses. But apparently, they are the ones we are calculating. But remember, on our formula, the short circuit power, the variable losses are going to be multiplied by K squared. So we are going to multiply 0.5 squared multiplied by PSC. You see that, right? So we can formulate an equation now based on that statement. Let's now try to simplify what we are having here, right? This is quite simplifiable. Cross multiply, that means we have 0.95 multiplying, that's in 0.5 times 250 times 1, that's 125 apparently. 125 plus P out plus 0.5 squared, that's 0.25 multiplied by PSC is equal to, right, again, 0.5 times 250 times 1, that's 125. So I'm not doing anything. I'm just simplifying this, what we're having here. I'm just simplifying this, right? We are just simplifying this, right? So that's basically what is happening. Nothing much is occurring. We're just simplifying what we have, right? So simplifying further, I can now divide by 0.95 here, divide by 0.95 on both sides. I end up having 125 plus PO plus 0.25 multiplied by PSC is equal to, right, 131. If I divide 125 divided by 0.95, I get 131.5789, right, 5789 etc, right, minus 125. I now subtract this 125 that I have here on both sides, right? I end up having PO plus 0.25 PSC is equal to, that will give me 6.579. That marks an equation. But my equation is how many unknown values? 2 unknown values. It means it's leading me to a simultaneous equation. Where do I get another one? At full load, I now know that K is equal to 1. So I simply substitute again. We were told that the efficiency is still the same. Even at full load, it's still 95%. So we can now say K is 1 times 250 times 1, right? Divided by, remember, that's our power factor. We were told the power factor at unity is unity. So cos of theta there is 1. That's our power factor, right? So simplifying that, we get again 1 times 250 times 1 plus PO plus PSC. Remember, our K now is 1. So it's going to give us 1 times PSC is still going to be PSC, right? Simplifying that, it means we have 0.95 multiplying 250 plus PO plus PSC is equal to 250. I divide again by 0.95. I divide by 0.95 is an option that I would want to take to end up having 250 plus PO plus PSC is equal to 250 divided by that. I get 263 is 250 by 0.95, and that gives us 0.95, and that's 263 actually 0.157, right? Transpose, divide by, so that's 263.158, divide, subtract 250, it means we end up having P out plus PO plus PSC is equal to 13.158. What's happening? We are now subtracting, transposing the 250, right? That marks our equation number 2. So we have two equations now, equation 1 and equation 2. So what do? We solve them now as simultaneous equations. We can take equation number 1 and make PO the subject. It means it's going to be 6.579 minus 0.25 PSC, right? We go to second equation, we substitute where there is PO with what we now have. So we can say 6.579 minus 0.25 PSC plus PSC that we already have is equal to 13.158. I have simply replaced 5 PO with what I have now, so it's solving of the spontaneous equation. So it means that when I have now 0.75 PSC is equal to 6.579. So I now divide by 0.75. I divide by 0.75, which means I end up having, divide that, it will give me PSC is equal to 8.772 kilowatts. So remember, that's where the kVA, we didn't convert that to kVA to VA. We just used it the way it is. So we knew also our answers are going to come out in kilowatts, okay? So therefore, it means even P out can be found. P out is therefore equal to 6.579 minus 0.25 times 8.772 that we now have, and that will give us 4.386 kilowatts, which means our two answers are out. P out, which is the constant loss, the constant losses, 8.772 kilowatts, and P out, our variable losses, they are 4.386 kilowatts. So we've arrived. This marks our answers, right? 3.3.2. 3.3.2 is saying the calculate the efficiency at 70% of the full load and 0.8 power factor lagging, right? So we are now simply substituting again into the formula. We now have PO, we now have PSC, remember? So efficiency is equal to KS cos phi cos theta divided by KS cos theta plus PO plus K squared times PSC. Efficiency is a ratio between the output and the input. And the difference between the output and the input are simply losses. And on a transformer, we have the constant losses and the variable losses. That's it. So PO, the open circuit power, is or are the constant losses. P short circuited power are the variable losses, right? So let's substitute K in this case. It means it's 0.7 or 70%. So we can say 0.7 multiplied by 250 times lagging power factor 0.8. We have substituted. Divided by 0.7 times 250 times 0.8 plus PO, which we now have 4.386, right? Plus K squared is 0.7 squared times 8.772. Right, so we end up having 94. Right, multiply that by 100 because it's efficiency expressed as a percentage. So we can simply say times 100 on what we have. Multiply that by 100, multiply that by 100, so that we get it as percentage efficiency at 94.159%. There we are. That marks our efficiency. Let's quickly go to the next question. Our next question was saying, question 4 is saying, state the 4 conditions that must be satisfied before 2 alternators can be connected in parallel, right? In order for alternators to be connected, before alternators can be synchronized, which means before they can operate in parallel, right? These are the conditions. Number 1, their EMFs must be the same. Their EMFs must be the same. Secondly, their EMFs must have the same frequency. And also their EMFs must be in phase. And also their EMFs must have the same angular displacement. These are the conditions that must be satisfied before 2 alternators can be connected in parallel. So let's go to 4.2. Right. 4.2 is saying a 3.3 kV 3-phase star-connected alternator operating at full load and a power factor of 0.8 leading has a percentage synchronous impedance of 4.5 plus J30%. Calculate the open circuit line voltage to which the alternator is excited. Okay, first things first, EP is equal to VP angle phi plus I times R angle of 0 plus IXL angle of 90 VP. Right. We have that information, so we can directly calculate 3.3 kV there that we are having, and we use that to determine that will give us EL 3.3 times 10 to the power of 3 divided by root 3, and we are gonna get 1905.256. Right, so that's 1905 there, 256 volts. Right. Then, in order to calculate IP times the RP, which are the phase current and phase resistance, right? The resistance per phase, we have to use, because we have been given the per unit resistance there from the formula. We have been given this the percentage synchronous impedance, 4.5 plus J30. So we need to know that the per unit resistance from that synchronous impedance, remember this is our resistance and of course inductance, so inductive reactance. So considering this one, 4.5, making it our per unit resistance, it's going to be divided by 100, which is 0.045, right? That per unit resistance is equal to this particular, so we are saying per unit resistance is equal to IP RP divided by VP. Right, so from this formula, I'm saying this is our IP RP as a matter of fact, and this is our IP XP as a matter of fact. Right, so making IP RP, it means therefore IP RP is equal to per unit resistance multiplied by VP. Right, so we can therefore substitute what we already have. 0.045. Where is this one coming from? We said 4.5 divided by 100%. Right, so multiply that by VP, which we have already just calculated, 1905.256, and that will give us 85 0.767 volts. That marks our IPRP, right? We repeat the same again per unit in reactance, PUX, the per unit reactance, is equal to IPXP over VP. Making IPXP the subject, it means we have per unit reactance multiplied by VP. What is our aim? We want to calculate EP from this formula. So these are the ones we are calculating, these ones, IP, RP, and IPXP. Right, so we can therefore take 30, that's 0.3 if we divide it by 100, divided by, and multiply by, so 30 divided by 100, that will be 0.3 multiplied by 1,905.256 as usual, and that will give us 571.577 volts. Right. So that is now our IPXP. Right. So we then go now to our formula EP. EP is equal to, right, 1,905.256. Now we had been told that the phase angle is 0.8 leading, right? So it means when we now present here, we say 1,905.256 angle of negative 36. Do take note there. Negative 36.87, right? Plus, we have already determined IPRP. IPRP, that's our IR as a matter of fact. Remember, these are PFA, so we have 85.757 angle of 0 plus, right, we take also 571.577 angle of 90, right? We convert them to rectangular one by one. So let's convert them to rectangular, right? The first one, 1,009 is going to be 1,524.203 minus J, 1,143.156. Right? That's the first one there. Plus, the second one is 85.757 plus J0 in rectangular. Plus, let's go to the third 0 plus J 571.577 in rectangular as well. So we add them now, real components on their own, imaginary components on their own. That will obviously give us 1,000. So that's 1,000 there. 1,609.94 minus J 571.579. Right. So that will now give us 1,708.394 angle of negative 11.546 to in polar, right? So converting that, using that now to calculate the line voltage. Remember, it's a star connection, so we can say root 3 multiplied by 1,708.394, and that will now give us 2,959.025 volts. Apparently, that becomes our EL. Let's look at the second question. The second question was saying the percentage voltage regulation of the alternator. So you just calculate the open circuit line voltage. That's how we calculate the percentage voltage regulation of the alternator, right? Percentage voltage regulation is going to be given by percentage voltage regulation is equal to EP minus VP over VP, right, times 100%, right? So times 100% there, right? That's 1,708 0.394 we have already calculated, minus 1905.256 divided by 1905.256, and multiply that by what? Multiply that by 100%, right? And that will give us negative 10.33 to 3 decimal places percent. That marks our percentage regulation, right? Let's go to the next question. The next question is saying 4.2.3. Calculate the load angle at which the alternator is operating, right? That's our question there. So how do we calculate the load angle? Right, I'm gonna answer this question using the vector diagram. Right, this is what we have. We have our IP here, and we do have our VP at this point, and then we have our EP. There is our EP, okay, and then we have our VP right here, right, and then this is marking our IP RP, and this is now marking our IPXP, right? These are the angles we have. That's our VP there. That's our EP. We did calculate our EP as 19.546. Point of correction there. It's negative 19.546, right? And then we did calculate we have been given our VP as 36.87. So what we are referring to as the load angle alpha is the angle between them. So we say 36.87, the phase angle that we have for VP. Why are we drawing it? Why are we drawing it in this way? Why not up? Because it's negative, mind you, and this one is also negative. So we are drawing them in this regard using IP as our reference. So we have to draw, assuming, of course, that's our vector diagram then. So we have 36.87 minus 19.546. And that will obviously give us 17.325. We are talking of this angle between the VP and the EP. That's the angle we have. That's our load angle, the alpha. We have calculated it. Let's quickly go on to question number 5. Right. Question number 5 is saying, name one way in which the rotating flux of a three-phase induction motor may be reversed. Now, in rotating the flux of a three-phase induction motor, what we simply do is we interchange the connection between any two supply conductors. So of the three supply conductors that we have, we simply swap or interchange two. So we just say by interchanging the connection between two supply conductors, right? Let's go to the next question. Our next question is saying the standstill EMF of a three-phase 50 Hertz 4-pole induction motor with a star-connected rotor is 300 volts between the slip rings. The standstill rotor impedance is 0.18 plus J1.2 ohm per phase. Calculate the torque developed at full load. That's our first question there. Right, so I'm going to answer that question. Right, rotor input, the rotor input is equal to 2 pi NT over 60. Right, that's our formula there. Right, so having known or having understood that, it means we can then use that to determine. So knowing very well, again, we have said that the rotor input is equal to 2 pi nt. So it means the rotor input is also equal. The rotor input is also equal to the rotor copper loss, right? The rotor copper loss over, right, over the slip, right? So we do have the slip. We want the rotor input. So we are going to calculate the rotor copper loss. The rotor copper losses are equal to 3 multiplied by I squared times R2. Right, so first things first, we'll first calculate EP. So EP is equal to 300, the voltage have been given, divided by root 3, right? So this is our VL. Is equal to 173.2, 173,205 volts, right? Then X2 is equal to S, the slip, multiplied by X naught, the open circuit reactance, right, which is equal to 0.0, that's our standstill as a matter of fact, 0.05 multiplied by 1.2, which is equal to 0.06 ohms. We do the same. Z2 is equal to R2 plus JX2, which is equal to 0.18 plus 0,06, which is equal to 0.189 angle of 18.435, converting it to polar, right? It means I2 is equal to S times EP over Z2, which is equal to 0.05 times 173.205 over 0.189, which is giving us 45.821 amperes, right? Therefore, the rotor copper losses equal to 3 multiplied by 45.821 squared multiplied by 0.189, which is going to give us, which multiplied by 0.18, apparently, our R2, right? Which is equivalent to 1133 point, that's in 1133.765 watts, right? Then rotor input, remember we said the rotor input is equal to the rotor copper loss over S. So it's rotor copper loss, the rotor copper losses divided by the slip. So hence we can now substitute 1133.765 divided by 0.05y, 5%. If we divide that by 100, we get that. So 22,675.3 watts. Therefore, calculating the speed, N1 is equal to 60 times F over P, the pair of poles. So it's 60 multiplied by 50 over 2, which is equal to 1,500 revs per minute, right? And right, making T the subject from the rotor copper loss, from the rotor input formula that we indicated from the start there, right? It means T is going to be equal to T is going to be equal to rotor input, right? Multiply by 60 over 2 pi times n1. Remember, we said rotor input is equals to 2 pi n1 times t over 60. Right, so making t the subject, substituting what we have, 22,675.3, multiply that by 16, divided by 2 pi, multiplied by 1,500. It means t is going to be equal to 144.355 Newton meters. Right, that marks our torque. Then 5.2.2 is now saying the full load power output if the friction and the windage losses are 900 watts. Right. Output power, the output power P out is equal to, right? So that's our output power there, is equal to rotor input, the rotor input minus the rotor copper losses, the rotor copper losses, minus the friction and windage losses, the frictional, which is the frictional losses, right? Now, substituting what we already have, it means the rotor input power, the rotor input we have just calculated it, it's 22,675.3 minus the rotor copper losses, we did calculate them as well. So we have 765 minus the friction losses we have them, that's 900 in total. So simplifying that gives us 20,641.535. So in kilowatts, it's going to be 20.642 kilowatts. That marks our 5.2.2. Let's go to 5.2.3, the speed at maximum torque, right? At maximum torque, the speed can be calculated. First things first, we need the slip at maximum torque. So the slip S is going to be given by R2 over X naught, which is equal to 0.18 divided by 1.2, which is equal to 0.15. Then N2, therefore, is equals to N1 minus S times N1, which is equal to 1,500 minus 0.15 times 100 and what? 1,500 again, right? So that gives us 1,275 revs per minute. Okay, there we are. Let's quickly go to the next question. So our next question is question number 6. 3 methods used to improve power factor, right? Number 1, we can use phase advancers. We can use also synchronous condensers or synchronous motors. We can use also capacitor banks or static capacitors connected in parallel with the supply. Right. Just out of interest, I might want to add on the phase advancers to say what exactly are they. So these are AC exciters. It's actually an AC exciter mounted on the shaft of an induction motor connected to the motor's rotor circuit. Right. So as to help improve the power factor, that's how it is connected in the circuit. Right. So let's go to 6.2. So of course, capacitors, these are just static capacitors, or the capacitor banks that are also used to correct the power factor. And then of course, synchronous condenser or synchronous motor, it is run at no load for a certain period of time in the circuit. It will correct the power factor, the poor power factor. Let's go to 6.2. 2.3 kV star connected alternators operating in parallel supply the following loads. Right, 50 kilowatts at unit power factor, 400 kilowatts, 0.9 power factor lagging to 350 kilowatts at 0.2 power factor lagging, 100 kilowatts, 0.2, 0.8 power factor leading. One machine supplies a current of 190 amperes at a power factor of 0.8 lagging, which means of our two machines, calling machine 1, machine 2, or machine A and machine B, it means one of our machines will already have the current that it is now taking, as well as the power factor of 0.8. Now, the first question is saying calculate the armature current of the second machine. That's our question there. There are two ways in which we can calculate, or we can perform that calculation. I will just explain the other one, and I will do one of them. But I will opt to do this one. You will just see which one you will favor, but I'll just do one here for the sake of time and explain the other one. How do you do it? Right. I'm gonna create a table here out of my own interest, right? And that's true power there, true power, and that's power factor, right? And that's phase angle, and lastly there is apparent power. Apparent power. There is my diagram. Okay, so I will just indicate here quickly. Okay, giving them boundaries there. There we are. Okay. There is my, okay. Right, true power, P1, marks my first power. I was told it's 50 kilowatts. P2, that's 400 kilowatts. P3, that's 350 kilowatts. And the P4, that's 100 kilowatts. Right. Cos phi 1 is equal to 1. Cos phi 2 is equal to 0.9 lagging. And cos phi 3 is equal to 0.8 lagging. That's the information I've been given. Cos phi 4 is equal to 0.8 leading. Okay, that's the information we have there. Right, let's start with phi 1. Phi 1 is 0 degrees. Phi 2 is negative. Why? Because it's a lagging phase angle, 25.842, right? Phi 3 is negative 36.87. Then phi 4 is equal to positive 36.87 because it's leading. Right, there is my information. Therefore, it means apparent power can therefore be calculated. S1, apparent power is equal to P over cos phi 1. So it's 50 over 1, and it will still give me 50 kVA. That's what I have there. And that marks my A1, S1. S2, it becomes in, again, 400 kilowatts divided by cos phi 2, which is 0.9. So it's 400 divided by 0.9, I get 444.444 kVA. Then S3 is going to give me 350 divided by 0.8, that's 437.5 kVA. All right, same applies. S4 shall give me 125 kVA, which is 100 divided by 0.8, right? Because S is equal to P over cos phi. Remember, right? So it has, that's apparent power for us, because apparent power, power factor cos phi is equal to true power of apparent power, right? So from there, what do? I then calculate the resultant kVA. The resultant kVA, which is ST, is going to be given by S1 plus S2 plus S3 plus S4. So it's 50 angle of 0 plus 444.444 angle of negative 25.842 plus 437.5 angle of negative 36.87 plus 125 angle of 36.87. There we are, which means therefore it's going to be converting 1 by 1 plus J0, right, plus 399.999 minus J 193.729, right? We've converted, of course, this to rectangular, plus 1 by 1, we are converting them. That the other one is 3, right? 437.5 angle of negative 36.87. If we convert it, it gives us 344.349, actually 0.999, which is 999,531. So rounding that off to 3 decimal places, it's going to give us 350. 350 minus J 262, so that's 262.501, right? We go again to the other one. 125 angle of 36.87 is 999.999, and that will give us, it's actually 99.999, and that will give us, that's 1,000 there. That's 100 plus J 75. Okay, so that's 99.999,586, etc. Right. If we add that, obviously we are going to get 899.999 minus J 381.23, right, which is then 977.412 angle of negative 22.957 kVA. That marks our ST, right? We then use that to determine SA. SA is equal to root 3 VLIL over 1,000. So which therefore is equal to, so of course SA, with the information that we are having, we can therefore you calculate it first. SA root 3 multiplied by 2,300 multiplied by 190 that we've been given as our IL, divide that by 1,000, and that will be 756.906 angle of negative 36.87, right, which apparently in rectangle is going to be 605.524 minus J 454.145, right? It means for the first machine, that's the information we have. So we can label this for machine 1. Machine 1. It leads us then to the second machine, for machine 2. So for machine 2, SB shall be equal to ST minus SA, because ST is actually equal to SA plus SB. So we are simply taking ST 899.999 minus J381.23 minus 605.524 minus J 454.145, right? Subtracting that, well, it will give us 294.475 plus J72.915, which is equal to 303.368 angle of 13.907 kVA, right? That's our SB. power of the second machine. Right. Now that we have SB, it means it's possible then to calculate the current of that SB. SB, as a matter of fact, is equal to 3 multiplied by VLIL over 1,000. So making IL the subject, it means IL, which apparently is also equal to IP, which is going to be equal to SB times 1,000 divided by root 3 multiplied by VL. So hence we can substitute 303.368 times 10 to the power of 3 divided by 2,300. 2,300 and so times 3. So that's root 3 there, right? And we are going to get 76.152 amperes. And there's a quicker way of doing it, which marks option 2, right? We would have used the power, each power P1, P2 that we're having to calculate IL1, IL2, IL3. How? We know that that power is equal to root 3 VLIL. So making IL1 the subject, it means we have P over root 3 times VL times cos phi 1. Because our formula is saying root 3 multiplied by VL IL cos phi 1, like for power P1, root 3 times VL times IL1 multiplied by cos phi 1. Right, so making IL1 the subject means we are going to say 50 times 10 to the power of 3 divided by root 3 multiplied by 2,300, which is 2.3 times 10 to the power of 3, right? Multiplied by, like in our case, for the first power, P1, it is a unity power factor, so we simply say multiply by 1. That becomes our 1. All right, so we'll get IL1 as 12.551 angle of 0 amperes. That marks our IL1. We repeat the same process for P2, using P2, P3, and P4. We also calculate IL2, IL3, IL4. Then we say IT is equal to IL1 plus IL2 plus IL3. Then we use, so it means now we are using the currents instead of using the power. As I have done, I was using the apparent powers there. So we could have just used the currents and it was still going to be easier directly to arrive. IL2 is going to be equal to IT minus IL1, where we are saying now IL2 is the machine, for the machine, is the one we are going to calculate using IL1. The one we are now calling our I1 is the 190 amperes that we have been given. And the IT shall be the one that we get after summing up, of course, vectorially, the currents we have, the IL1, IL2 that we have calculated from this. Please take note, this IL1 that I'm talking about is the one we have been given. So let's call it, we can call it IA so that we don't make a mistake, and we can call this one IB so that we don't make a mistake, whereby we are now saying this is the current for the machine B, this is the current for the machine A, and IT is the one we are now calculating using the currents for each machine from the example that I've just highlighted here. It's one method of doing it. Right, so having said that, let's quickly go to the next question. 6.2.2, right? 6.2.2 is saying calculate the power factor of the second machine. The power factor of the second machine can be calculated using the phase angle for the second machine. PF is equal to cos 13.907, which is 0.971. Already we had made that calculation. So we are simply basically using that phase angle that we have just determined, 13.907. Right, so let's go to the next question, 6.2.3. What is it saying? P is saying calculate the output power of the second machine in kilowatts. So P2 for the second machine is going to be equal to root 3 VLIL2 multiplied by cos phi 2, where we are saying this is the current for the second machine. So we'll say root 3 multiplied by 2.3 times 10 to the power of 3, of course, multiplied by 76.152 multiplied by 0.971. Right, so if we substitute that, it's going to give us 294.570 kilowatts. That marks the power, the output power for the second machine. Let's quickly go on to the next question. Question number 7 is saying, define voltage regulation of a transmission line. Right, it is a rise or fall in the receiving end voltage when full load is switched off, provided the sending end voltage remain constant. That's in our voltage regulation of a transmission line. It might interest us just to know out of interest that when it comes to the transmission lines, there is a difference between the sending end voltage and the receiving end voltage. Why? And oftenly it is such that the sending end voltage is greater than the receiving end voltage. Why? Because of the losses that have occurred in between due to the inductance and the resistances in between the transmission lines. So those cause a loss, and those losses will result in the difference between the voltage, the sending end voltage, and the receiving end voltage, where the sending end voltage is always greater than the receiving end voltage. Is good to note that, right? So here comes a question. It's saying a long overhead transmission line supplies a three-phase load at 133 kV, 50 hertz. The following information with regards to the line is known. Receiving end current IR is equals to 87 angle of negative 36.87 amperes. Resistance per conductor, that's what we've been given. Inductance, inductive reactance per phase, capacitive reactance to neutral. We have been given. Use the nominal T method to answer the following questions. First, draw a neat, fully labeled circuit diagram of a T method used to solve this question. Right. Oftentimes, even if this question is not asked, I advise that you first draw the diagram. It serves you very well to be able to know what exactly which values exactly are you going to be using, right? Here is our diagram. This is how it looks like. So mark my resistor here. There is the inductor, right? And then we have our capacitor here connected in parallel. Then of course, okay, then we have again, there is our resistor there, there is our inductor there, right? And then this is what we are having. Okay, right. We will label this one, right? I'm going to be calling this, okay, this point here. Let's start with this point. This point is A, and this one is B, and this one is C, this one is D, this one is E, and this one is F, right? And I am going to refer to this as RP. As a matter of fact, I'll be referring to all these values as P to try and put an emphasis on the fact that we are dealing with phase values, the values from per phase. Instead of line voltages or line currents, we are dealing with phase currents, phase voltages, etc. Right, so I'm going to call this RP. So do not be amused. Oftentimes, some schools of thought, some scholars, what they do, they just refer to them as R, they refer to IS, the sending end current, they refer to IR, the receiving end current. But I will be referring to the receiving end current as IPR. I will be referring to the sending end current as IPS to try and put much more emphasis on that fact that we are dealing with phase values. So if you can adopt also to just not doing that, to say IS what I is, so it's still good. You can still do that, right? So that's RP there. RP now. RP is equal to R total over 2. So what is our total resistance then? Is 25. So divided by 2 to give us 12.25. Same applies. X LP is actually equal to X L divided by 2. So that will also be 40 ohms because it's given as 80 there from the information we read. Same applies, it repeats itself here. Our RP again is equal to 12.5, and our XLP is equal to 40 ohms. Right, because we've divided them by 2. Then let's go to our capacitance. XC is equal to 1,600 ohms, right? And then here we have VP in between. So I will indicate this is my VC. That's VC. Apparently, that's also VBE there. VC is the VBE, right? And then here we have the sending end voltage. This is marking our VPS. We are calling this the sending end phase voltage. And this is marking our receiving end phase voltage. I'm going to call it VPR again. Remember, I said I want to put emphasis on understanding that these are phase values that we are dealing with, or values per phase, right? So let's now indicate the current. This current here is IPR. That's IPR, the receiving end phase current. And I will indicate this one as my IPS, the ascending end current, phase current. And then I will indicate this one as my IC, right? This is our diagram. That's how the diagram looks like. This is the diagram that the examiner is asking for, right? And that's the T, right? Remember, we said this is a greater value. This one is greater than this one always, due to the losses that have occurred in between, due to the resistances and the inductances in the circuit or in the transmission line, right? So let's now perform calculations. What are we looking for? We are looking for the sending end current, which is this one. Right. I want to explain first. So the diagram is good. No wonder I was saying, even if had the question not asked to draw it, it was good to draw it so that you can guide yourself on what is happening. We want IPS. And IPS, remember, I said even if you say IS, you are still fine, no problem. But don't forget we are dealing with phase values, right? So IPS is equal to IPR plus IC. It means these are the two that need to be calculated. Why? Because according to Kirchhoff's first law, current entering a junction is equal to current leaving the junction. So it means this is true, right? Now we need to find IC. So IC can actually be found by saying VC, which is VBE, divided by XC, of course, the capacitive reactance that we have. That's IC. Then coming to IPR, it means IPR has to be calculated using the voltage VBC divided by ZAB. So those are the values that we need to calculate there. Right. So hence, for that reason, we can start there at the values of ZAB, ZBE. Let's start from there. Right. So I will start to calculate ZAB first. Let's calculate ZAB. ZAB is equal to 12.5 plus J40, right? That's our ZAB there. We are talking about this impedance here that we have here at this point here. And apparently ZAB is also equal to ZBC. They are equal, the two of them. Right, from our diagram there, we are saying the impedance between B and C and the impedance between A and B, they are equal because those two values are basically the same. So we are saying it's 2.5 plus J40, which converted to polar is going to be 41.908, angle of 72.646, right? That's in ZAB there. Let's go to ZBE. ZBE is equal to, right, that's apparently ZC, this one. ZBE is also the same as ZC. It's the same thing, right? It's equal to 0 minus JXC, which is 1,600, right? Converting that to polar is going to be 1,600 angle of negative 90. There we are. Right, and then it means now we can calculate VPR. VPR is equal to VLR over root of 3. Remember, on the information we have, given that is 130 bright, so it means we have been given the line voltage, and as it stands, that's the line voltage at the receiving end, right? So, and we can now calculate 133 times 10 to the power of 3, divide that by root of what? Root of 3, and that gives us 787.586 angle of 0 degrees, right, which is going to be equal to 787.586 plus J 0, right? That's VP R for us, the phase voltage of the receiving end, right? It takes us therefore to IPR. Now for IPR, we were told IR is equal to that. So I said often the examiners and even some textbooks, they are using IR, XL, XC, etc. Let you not be confused by what I'm doing there to say PP. I'm just putting emphasis on the issue of the phase, right? So 87.86, I just want to emphasize on something again. Oftentimes, sometimes they won't give you this. They give you the power. They say, given that the power is such and such, you can use that power to calculate IPR, this one that we've been given, and apparently it is also equal to ILR, assuming or making an assumption that obviously our transmission line is not in star connection because it's the most common connection that is made. Right? So IPR is equal to, right, 87 angle of negative 36.87. We've just taken it there, right, from the data that have been given. So changing that to polar, to rectangular, that will be 69.59990,675, which is the same as 69.6 minus J52.2, right? That marks our IPR in amperes, right? Let's go to the next. So what is the next calculation? The next thing is we want now to calculate VBC, the voltage across the 2 points B and C, which are these ones, right? We see them, this one and this one. So we want VBC, right? So VBC is going to be given by IPR that we've just calculated, because that's where IPR from my diagram is. You see that? That's where IPR is actually. That's here. Right, so it's IPR multiplied by ZBC, of course. Right, so IPR times ZBC, and we have already calculated ZBC right there on top. So we can now substitute 87 angle of negative 36.87 multiply 41.908 angle of 72.646, and that will give us 3,645.996 angle of 35.776, right? And that will now give us to rectangular, that's 2958.029 plus J 12,131.514. Right, we have VBC. Where are we heading? We have IR, remember, and we already have IPR, so we are fine. Remember, we want IP as the sending end phase current, but then we don't have IC. So in us calculating VBC, we want to use Kirchhoff's second law to say this VBC that we have, the voltage across the points BC, and the VPR, the voltage that we have, if we add them, they should give us VC, right? Logic might try to deceive you and think that, no, man, we are supposed to add VPR because according to Kirchhoff's law, we are saying the EMF in any closed loop is equal to the voltage, the potential difference within that loop. Remember, we are going towards this direction where there are bigger values. So it means the VC is bigger than VPR. So we have to say VC is equal to VBC plus VPR. So that's where we are heading. Right now, we have just calculated VBC. So now we want VC. Why do we want VC? So that we can calculate IC. Why do we want IC? Because that's the one which will give us IS, the sending end current, right? So it means VC is equal to, from the small explanation that I'm giving there, is equal to, and as a matter of fact, the VC is the VBE, remember, don't forget. It is the VBE, the voltage across the 2 points B and E. So it's VPR, right, plus VBC. So I was trying to explain why. Please do take note. You add because you are working from a smaller voltage to a bigger voltage, right? So now we are adding the 76,787,586 plus J0, right? Plus right, 2,958.029 plus J 2,131.514, right? Adding those two, they will obviously lead us to that's in 79745.615 plus J 2131.514. Converting that to polar, that will be 79774.07096 angle of 1,531, right? So it means now we have VC. So it means we can use VC to determine IC, right? So IC is equal to VC, remember that's VBE, right? Over ZBE, the voltage across the capacitor, right? So VC 79774.096 angle of 1,531, right, divided by ZBE 1600 angle of negative 90, and that gives us 49.85881, which is 49.859 angle of 91.531. We just divided these and we subtracted. So we had 1,531 minus 90, that's giving us 91.531, right? So that will also give us in rectangular minus 1.332 plus J 49.841. Okay, let's now go to IPS, the sending end current. Therefore, it means it's possible now to calculate it. The sending end current is equal to IC plus IPR, we already have it. So it means it's minus 1.332 plus J 49.841, right? Plus 69.6 minus J 52.2, right? And that will definitely give us 68.268 minus J 2.359, which is equal to 68.309, angle of negative 1.979 amperes. That marks our sending end phase current, which is the same as also the sending end line current. So that's our sending end current there. We have determined it. Right, let's quickly go to the next question. The next question is now saying calculate the sending end voltage. So for the sending end voltage, the sending end voltage is going to be equal to that's a VAB first. Right, let's first explain how do we find that sending end voltage. Sending end voltage is going to be, is this one, VPS. It's equal to VAB, the voltage across this, plus VC. Why? Because together they are now in a closed loop. According to Kirchhoff's second law, the voltage in a closed, the EMF in any closed loop is equivalent to the sum of the potential difference. So our potential differences in this case, they are AB and the VAB and VC, right? So VC we already have it, no need to calculate. We are now calculating VAB. So you can even sense VAB is going to be equal to IPS because the sending end phase current is the one passing through AB multiplied by ZAB, and apparently ZAB is the same as ZBC. So let's calculate it. Right, so it means therefore VAB is equal to IPS, the sending end phase voltage, the sending end phase current multiplied by ZAB, right? Which is equal to, right, the sending end phase current, we have it 68.309. Angle of negative 1.979. We have just calculated that. Multiplied by, which means ZAB. And as a matter of fact, ZAB is equal to ZBC. They are actually equal. So we can say multiply by what? 41.908, angle of 72.646, right? Which is equal to 2,862.694, angle of 70.667, right? And that in rectangular is going to be 947.718 plus J 2701.268. So it's just a matter of converting that with the calculator, which means the VPS, the sending end of voltage, is equal to VC plus VAB. But do take note, this is the phase voltage we are about to calculate, which means we are going to multiply it by √3 so that we now have the line voltage, right? So we are now taking 79745,615. That's our VC, by the way, plus J 2131.514 plus, right, plus VAB, that's 947.718 plus J 2701.268, right? And what do we get? That gives us 80,693. That's 80,693.333333 plus J 4832.782, right? Which is equal to 80.837.923, angle of 3.427, right, volts. That marks our phase sending end current. However, we haven't determined the line voltage. Therefore, the sending end line voltage is equal to √3 multiplied by 80.8 37.923, which is therefore going to give us 140015.39 volts. Apparently to kilovolts, you just press the ENG button once there, you get 140.015 kilovolts. That marks our sending end current. All right, let's go now to the last question, which was saying calculate the sending end power factor. So the sending end power factor cos phi s is equal to cos 1.979, right, plus you are just adding the phase angles there, 3.427, and that will now give you 0.996 lagging. There we are. So this marks the end of our revision of our paper. This is how we do it, okay? Just like that. All right.